Today we're going to be looking at indicator functions, which is a handy mathematical notation that proves especially useful when dealing with probability problems. The basic definition of an indicator function is pretty simple. We're going to use a Blackboard boldface 1 to denote the indicator function. And as an argument, the indicator function takes an expression which is either true or false. When we run that expression through the indicator function, it returns a 1 if the expression is true and 0 if it's false. For example, if I look at the indicator function of 3 less than or equal to 5, that would be 1, because that's a true expression. On the other hand, if I look at the indicator that 3 equals 5, that would be 0, because that's a false statement. Now, when we take the indicator function and give it an argument, it turns into a function that we can graph. So for instance, if g of x is the indicator that x is less than or equal to 3, then for values of x which are less than 3, the indicator function evaluates to 1. So it's 1 right up until the point that x equals 3. For x values bigger than 3, 4, 5, etc., the value of the indicator function is 0. So this gives us a very handy way of describing this sort of step function that without this notation, it would take us 2 lines to develop. Now here's some uses of indicator functions. Indicator functions are especially useful for probability applications. Oftentimes the densities that we deal with in probability have one value over one region and another value over another. For instance, consider the following density. F at s is e to the minus s if s is greater than or equal to 0 and 0 otherwise. This is the density of an exponential random variable with rate 1. Now, I had to use 2 lines in order to write this density, and mathematically this is a little difficult to work with. I'm continually having to break things into cases. But I can write this with just 1 line using indicator functions. This is equal to e to the minus s times the indicator that s is greater than or equal to 0. Now see what our indicator function does for us? If s is greater than or equal to 0, I'm just multiplying times 1, so I get back my e to the minus s. When s is less than 0, then I'm multiplying e to the minus s times 0, and I get 0. So this expression and these 2 expressions are, in fact, identical. Let's look at another example. If u is a uniform random number over the interval from a to b, then the density of u is going to be 1 over b minus a if and only if our dummy variable is in the closed interval from a to b. We can write that using indicators as the density of this random variable u at x is equal to 1 over b minus a times the indicator that x is in the closed interval from a to b. That gives us a nice way of describing densities where we don't have to worry about using 2 different lines. Now, when we use indicator functions to describe our densities, we then have to understand how indicator functions work inside of integrals. Because, of course, we need to do integrals in order to find probabilities of events and expected values of events, things like the variance. The way it works is that the indicator functions change the limits of our integral. Let's do some examples. Suppose that I wanted to integrate from minus infinity to infinity x indicator x greater than or equal to 0 e to the minus x dx. Well, this function is going to be 0 whenever x is less than or equal to 0. So we don't have to worry about doing that part of the integration. That part of the integration is just going to be 0. We're only worried about values of x greater than or equal to 0. So that tells us that we can turn around and make the lower limit of our integral equal to 0. So this is the same as the integral from 0 to infinity of x e to the negative x dx. And now that we've gotten rid of the indicator function, we can proceed normally. Now sometimes it's helpful to go in the opposite direction. Suppose that I wanted to write the integral from 0 to 1 of v dv as an integral from minus infinity to infinity. Well, I only want the integral to count values of v, where v is between 0 and 1, so I can use the indicator function to write this as the integral of v times the indicator v is between 0 and 1 dv. This allows us, with the indicator notation, to drastically simplify our formulas and calculations in probability problems. Now there's an alternative notation for indicator functions that's useful in some situations. It goes as follows. If you see an indicator function, so blackboard boldface numeral 1, with a subscript that is a set, then the indicator function evaluated at x is equal to what we've been calling the indicator that x is inside the set A. So with this sort of notation, if I wanted to write e to the negative s if s is bigger than or equal to 0 and 0 otherwise, this would be written with this new indicator notation as e to the negative s indicator. S has to be between 0 and infinity. And it's actually inclusive on my 0, so I'll have a square bracket on that part of the interval. So it's really just another way of describing the indicator function.